going to put an elevation map where the width of each bar is 1. Compute how much water you can trap. So you can think of this as a mountain range. And in a mountain range, water can only be trapped in the valley. So the valley is a place that is lesser than the mountain. So if you look at this image, for example, the position at index 2 is lesser than the boundaries on the left and the boundaries on the right. So you can consider these boundaries to be mountains, all right? Now that I've established that you need boundaries in order for you to trap water, let's look at the brute force approach of solving this problem. Now, if you're currently at index 2, for example, you need to find the maximum to your left, maximum to your right, then take the minimum and subtract from where you're currently at. Okay, imagine this. You're at index 2, for example, where the height is 0. The maximum to your left is 1. The maximum height to your right is 2. If you take the minimum, it is 1, and you subtract it from where you are currently at, which is 0, that will give you a sum of 1, which is a value of 1, a unit of 1. You trap 1 unit of water here. And the reason you are taking the minimum and not the maximum is water can only fill to the level of the minimum, or else it will overflow. Essentially, you have to repeat this brute force approach across every index of this elevation map, and that will require a runtime of n squared. As you can imagine, that's not an efficient algorithm. The question is, can we do better? The answer is yes. The answer lies in pre-computing the maximum to your left, maximum to your right, and store it in 2 separate arrays. In my approach, we're looking at storing 2 maximums, right? The left max and the right max. So the question we're asking at every point in this elevation map is, wherever you are at, what's the maximum you've seen so far to the left and to the right? So from here to the left is 0, from here to the here is 1, to the left is 1, from here is still 1. So this will produce this, and if you go from here to is still 1, then it's 2, then this produces this. So let's take, and now at index 2, right, which is 0, and minimum of the maximums, which is minimum of 1 and 3, will be 1 minus where you're currently at, which is 0. That will be 1. So it still gives us this trap water. But what I want you to notice is, in this right max, the comparisons we're making is not the immediate. We're not making the immediate. So this one is saying the right ones at index 2 is saying the maximum to the left is 3, which is true, and the maximum to the right is 1, which is also true. But it is not the immediate, and it's not necessary to be immediate as long as we have a minimum. And in one final sweep, you can go through the array of the maximums, obtain the minimum, and subtract height from the minimum. In order to save a bit of time, I'm pre-written the code. Feel free to pause this video if you want to write it. So we have a variable n. It holds the length of the elevation map. Then you have the right and left index, which will hold the left maximum values and the right maximum values. Then L max are just values that will hold the maximum you've seen so far on the left and right respectively. As you can see here. Then we're going from left to right in this array of this elevation map, yes? And you are just obtaining the maximum and inputting it where you're supposed to be. And because you can go from left to right, you can also go from right to left at the same time, okay? Which is why this J stands for, all right? And in one final sweep, we hold a water variable which will hold amount of water we've been able to trap. Then if in one final sweep, you can go from the range, because of the values are the same, right? The arrays are of the same size. You can obtain the minimum of the maximums, which is this, and subtract height from it, and which is that. So you can add it to water, and then you just run this. It works. This algorithm has a runtime complexity of O of n and also a space complexity of O of n. So the question is, can we even do better in terms of the space complexity? And the answer is yes. To achieve a space complexity of O of 1, we can use 2 pointers. These 2 pointers would help us track the maximum on the left and right, and then these maximas can then be utilized to give us information about where water can be trapped. Again, we have a maximum, so you initialize a maximum to the end positions, right? On the right max, and so the left max in this case is 0, the right max is 1. So if you look at it now, this is the minimum, right? This is the minimum boundary, all right? So if we shift this here, all right, because this is the minimum boundary, you can obtain, you can come, because you tend towards the minimum boundary, right? Like we did previously, you select the minimum. If you update this and subtract 1 from the L minimum, which is 0, it will be negative. So we don't update the water, and you just keep this here, okay? And then now this is now at 1, and the next index at the next iteration, these both are equal, right? The left maximum now is 1, right maximum is 1. So it doesn't really matter which one you shift. You can shift this one to have the same result. But just for consistency, I'm just going to shift the left one for now. Now, I'm shifting this one here. So this will be, where you're at now is 0, right? So, but the left maximum is 1. So 1 minus 0. So that's why you can add it to the water. All right. Then the next iteration, of course, the left maximum is still 1. All right. But the right is also still 1. So you can shift this. All right. Don't forget, now shift this. So now the boundary, the minimum now is 1, right? Don't forget the minimum left maximum is still 1. So 1 minus 1 is still 0. So it's not useful. So then we can shift this. All right. So you keep going like that. And that's how you solve that problem in O of 1 space. You can use these slopes to imagine which pointer to shape. Whatever direction it slants towards, that's the one you shift. All right. And if it's equal, you can shift either one. It's fine. Of this problem in O of 1 space is actually quite straightforward, and here it is. So of course, this is our left pointer initialized, left maximum and right maximum initialized to the initial the pointer indexes, and water variable to hold trapped waters. And don't forget your while left equals to left greater than left, while left less than right condition, essentially saying you don't want things to cross. You don't want your pointers to cross, because if it crosses, it loses its relevance. So this was the logic I was trying to demonstrate before. While let's increment it, then obtain the maximum. So doing this process, it eliminates the probability that you're going to have negative values. So you can then subtract, and that's how you solve it. I'm just going to submit just to show you that it works. And as you can see, it works. So that's how you solve it, guys. See you next time. Bye-bye.